You, can you hear me now? Okay, yeah, okay. I was totally muted. You're right. I did not see that. I'm sorry. I'm gonna do that all. Maybe I'll do that all over again. I'm sorry. I was totally muted, but you can hear me now. Yes, I was totally muted. Okay. Oh my God. Um, and then I think you deserve the good mornings again. I don't know. I think I need to. Oh wait, no, there's more people here. Sorry. Okay. So what I was saying that you missed when I was muted was good morning, Daniel. Good morning, David. Good morning, Luna. Good morning, Noelia. Good morning, Nikaya. Good morning, Jitlali. Good morning, Alyssa. Good morning, Darina. Hi, and good morning, Amarani. D morning, Catherine. Good morning, Daniel. Okay, and now right. Okay, now we're Catherine. Right. Okay, I'm going through the chat. This whole chat thing. So okay, and morning. Okay. Oh, and good morning, Aja. Sorry, and good morning, Molly. Sorry. Okay, I think that's everybody. Okay, it's yeah. Okay. The funniest thing. No, it's not funny. I'm not going to say it. All right, we're just going to get rolling. Okay. Okay. So it's physics. So we have spring break soon, and then you have an exam, and everybody's very good on the homework. You guys are great. I'm now maybe one. If you handed anything today, I haven't seen it, but up until last night, I think I saw it. It's lovely. Okay, I think we can get right down to business. Oh yeah. All right. And I'm going to get today. I'm going to re-summarize what equations I think we have so far. At some point today, we're just keeping a running list like for 2 semesters. And not it's not really because you have to memorize them ever. It's because it's like what we know. But anyway, but I want to. So the question of today. Hopefully, there's going to be a lot of discussion today. Hopefully, this is not going to. Hopefully, we're going to break through a wall today. Not anyway. So a question on the table. I just want to throw out there. And there's various ways to do this. It's the same question we've sort of been doing for days now, but this is kind of like more people coming. I'm sorry. So the question that's on the board right now, right? Like any and all of you could get rolling on this right now if you want. And at any moment in the class, I will happily accept answers in the chat or in voice or in private chat. I'm not going to say the answer to this just yet. And I'm not even going to start walking through it just yet. I'm going to say some other things, but it is the question for today is if we drop a rock from rest, and again, hopefully you recognize this question. Like hopefully you're almost thinking this is getting a little repetitive or something, but that doesn't mean, and maybe even many of you already know how to do this question because like we have done it. And maybe many of you know how to do it with equations. Maybe some of you can do it without equations. Maybe many of you do it different ways. And in fact, I'm going to show you further different ways to do it. So it's not meant to be a trick or meant to be any weird kind of challenge. But I will say this question, this kind of question that's on the board right here, I'll read it out in a second, but this question that's on the board right here, it has like the nice, tidy, simple flavor that I like physics to have. Like it feels to me like the kind of question like you'd think you'd be able to answer in physics, right? To me, it seems fair. It's like, not a lot of complicated information to assume, not a lot of unrealistic information to assume, not a lot to keep track of, but yet still a question that requires a little bit of thought to do. So I use this as a symbolic, like how far have we come in physics kind of question, in that I think right now, honestly, good morning, Yasmin, awesome. I think right now there are some of you that already know the answer to this question, and you can put it in the chat if you want, or you can hold still for a second. But I absolutely believe there's some people in the room that have already figured this out on a piece of paper or in their heads, or feel they just know it. I'm willing to believe that. I think there's some people in the room that could get it, but haven't yet because I'm talking or something, or like once I tell them to, if they sit down, they'll do it and they'll get it right. I believe there's some people in the room that would try and might not get it right yet. And all of this is fair. I mean, all these are totally like fair places to be in the class. I believe there are some people in the room, even right now, that even if they think it's sort of a fair question, whatever, if I said go, everybody get an answer right now. I do believe there's some people in the room, even listening to me right now, who would be stuck and be like, I actually don't know what to do. I don't know how to start this. And that's also fine. I mean, for now, like I don't want that to be true even at the end of the semester, but that's fine. But the reason I think it's a good question for me to address to all of you, like I want to talk about this type of question with all of you, is that even those of you who already have an answer, or are pretty sure you already have the right answer, or can figure it out pretty fast, I do want those of you to be able to drill a thing like this. Like our ultimate goal is, yeah, we want to be able to get an answer to this question, but not even just by being so handy with equations that we can plug in and square things and get it. Like, again, I believe there are some people that can already do that with this. I want all of us in the room to get to the point where a question like this, we can do in our head. We can do in our head and have perspective on the answer, like get an answer in. This is ultimately now, again, so I'm talking to all of you, but I'm not, everybody's at different stage, but I'm saying the goal, if you like really want to go somewhere with this physics, the goal is to be able to take a question like this and actually be comfortable enough to do it in your head and check the answer, like get an answer and then be like, now, does that actually make sense compared to other things I know? Like, I just got the answer like 11 miles or something. Is that realistic? 11 miles, or should it have been 11 meters? Like that kind of thing, right? Now, again, to some of you, if I heard this, and by the way, I think I can do this in my head. Like I think, well, I'll say, I think, for example, I don't think the answer is 600 meters. I'll say that. I don't think the answer is 600 meters. I do think, in fact, the answer is, should I say, I think it's more like 18 something meters. I think there's an 18 involved. Maybe 1800 or 18,000 or something like that. I also think the number, I think it is more than a mile. If you want to, like, so those of you who already do have an answer to this, play with it. If you're pretty sure you know the answer, because you, first of all, see if you can do it without formulas, see if you can actually logically do it in your head. And again, those of you who don't have an answer, it's fine too. We're going to talk about it. But those of you who have an answer already, first of all, see if you could get that answer. Like, did you get it in your head or did you get it with a formula? But another thing is too, maybe try a little unit conversion. Like, do you think this answer is greater than a mile? It's about time I read the question, I guess. I'm sorry, I'm being sort of a jerk. The question is, you drop a rock from rest. From rest, by the way, that means initial velocity 0. And that literally means drop. Like, I'm almost being redundant, but because that's as opposed to throw down or as opposed to throw up, both of which are also possible, and we can do physics questions about those just as easily once we do this. But right now we're saying drop, so that assumes initial instantaneous velocity of 0, like v naught equals 0 is what that means. Okay, and someone just else came in, sorry. Oh, and there's someone in the chat, sorry. And then I'm saying, let this rock fall for a minute, like 60 seconds. Actually, whichever way is easier for you to think about it is fine. But you let this rock drop for a minute. Now, it's a rock. I'm trying to be so it's not a feather, it's a rock. So you don't have to get all caught up in any kind of aerodynamic weirdness. Like, just it cuts through the air off a building or something for a minute. How high would that building be if it just landed on the ground at the end is the question. Put another way, if you drop it from a super, super high cliff, I think there's 2 people waiting in the waiting room. I'm sorry, hold on. Sorry. Like, give yourself a cliff like way above the ocean or something in some island where you've got all the room in the world. You drop this thing, wait a minute. How far has it actually fallen? Now, the assumption behind this question is that there's an answer. It's like earlier in the year, and there is an answer. And maybe on a really windy day, the answer that you get might be like a couple centimeters off the actual realistic thing, but only like a couple centimeters, whatever answer we get right. And I'll be, good morning. So, good morning. Sorry. Hold on. I just want to also make sure I'm not. Thank you. Yes. Sorry. No, awesome. And I like this, that people, yes. Good morning, Yasmin, and good morning, Ashley. Awesome. Sorry. I'll keep talking about it. So for this question, I think it's like realistic. I think like whatever the math gets you is pretty much what would happen in real life if you could find a cliff high enough to do this. Now, how high? Well, that's what we're asking. Like, how far would something fall in a minute? Now, you can break this down because, this is all based on what we did on last class and the class before that. Like, you definitely have all the equations and numbers you need, and I will rewrite them again in a second, but I actually am trying to push us all forward in a way. I want to get used to these equations. I want to get to start to know these equations, but I also want you to see simultaneously that the equations are just shorthand for logical ways of thinking. They're just like faster ways of writing logical ways of thinking. And some of us are faster at that logical way of thinking without the equations and some with, and either way is fine. But like, for example, this question here, which again, I'll start to take answers at any time you want to give them to me, but I won't say if they're right or wrong. So at any moment, anybody wants to put an answer to this in the chat or whatever, I mean, maybe the private chat is better, but I'm not going to say whether the answers are right or wrong. So it shouldn't really affect anybody else's thinking. But this is the question on the table, again, right here. You start thinking about it however you want. Look back in your notes from last class. I'm going to start writing equations down and breaking it down. First thing I'll say is, if you want to know how far something falls in a minute, you might start with the question, okay, how far does it fall in the first second? In 1 second, how far would this fall? And that is precisely problem number 2 from sheet 5 or whatever, that problem that we actually kind of did for 2 days. And I know I'm always rushing at the end, and that's why I'm trying to go slow now. But for 2 days, we did this problem called the first second, and it was about a bicycle. The bicycle had an acceleration, a constant acceleration of 2. And we figured out an answer. And the answer was not 2, but we figured out an answer. Here, we don't have a bicycle. We're dropping something in free fall. One lesson I'm trying to say from all of yesterday, if you're like trying to put this all together, excuse me, not yesterday, Monday, is that when something's in free fall, it has constant acceleration, just like the object in that example from homework 5. Excuse me. When something is in free fall, the extra secret special knowledge that we automatically have about that object, if we say it's in free fall, oh, and I should even say here, I'm saying let it free fall. Like I do mean free fall. When anything is in free fall, we know that it changes its velocity always. It's always speeding up or slowing down when it's falling. Like nothing falls at constant velocity, but everything falls at constant acceleration. This is the lesson we're trying to say. I'm trying to say that that's qualitatively a very big point, but quantitatively, it's also a very specific point. When it comes to free fall, things free fall at a constant acceleration rate of 10 meters per second squared. Like I will write that again in a moment, but I'm also just trying to, like, if someone says free fall, you automatically know V is not constant. V is changing all the time, but it's changing at a constant rate called A. And that A is 10 meters per second squared, like approximately, but very realistically, like very legitimately, approximately 10. Okay. Now I'm going to say I just got one private message with a possible answer for this question. Because it was a private message, I'm happy to, and that was a good choice. I'm happy to say, oh, I think I just got 2. Okay, I'm going to say I just got 2 private messages with answers in them, which I'm very pleased. And those people should definitely submit for points and blah, blah. Like they should definitely put this in the 75 portal, no matter if I say their answers are right or wrong, right? They just gutsily, and it is, and I'm glad they're doing it private right now because it doesn't affect anybody else. So I just got 2 answers in the private chat, and I'm tempted to even say whether I think those, I guess I could say whether those answers are right or wrong, since they're private. But either way, they should submit them for points, whether I say they're right or wrong. So I'm thinking, I might not say just yet, but I'm totally acknowledging I just got 2 answers in the private chat, and I want answers from everybody eventually. I do, and I will walk it through. I'll say this, the 2 answers in the private chat. Oh, here's a weird paradox. I'm not going to say if they're right or wrong, but I'm definitely impressed by both of them. They're definitely both not crazy, and they're both the same. I'll say that. Both answers in the private chat are, so they're either both wrong or both right. Oh, I just got another answer in the private. Oh, it's so much fun to be me right now, in a way. Oh, now interestingly, okay. Now I'm starting to get different answers in the private chat. I will say I've got 4 answers in the private chat. Again, every single one of those people should be, look, everybody should be pleased with themselves. We're all here, we're all happy, but everybody who's put an answer in the private chat should be pleased with themselves and should submit it for the 75 point thing. They should, because they just took a risk and they all just said something that I'm going to ultimately say if it's right or wrong. And it is ultimately right or wrong, right? So I just want to pause and dwell in this happy space of trying physics. Like really, like if you're trying to do this problem right now, by any means, and I'm going to I do feel that I've technically walked us through it in a way, but I don't feel sufficiently. Okay. This is not a test. This is not a test of you guys, like whether you're learning or not, because I don't think that I've fully taught this yet. I mean, but I do think you have the tools in front of you. You can do it any way you can try. And also, honestly, for many of you, one of the reasons I'm continuing to ask this kind of question for like 3 days in a row without putting up the equation stuff yet is I really want all of you to try it, because the truth of the matter is some of you will get this wrong, but if you get this wrong and you see why it's wrong, and you see why the right thing is right, you will get the right thing much better than if you just hear the right thing and never saw how it compared to the wrong thing. I can't put that any better. So it's really not like, so if we really get past right or wrong, or we really see how we would think of this on our own, and then I show you how I think of it, it will much more help you. Like, you'll be able to build a bridge between how you think and how I think on this. If you know, like, you don't just want to know that you want to get to me, you want to get from you to me in terms of physics understanding, right? So it's really important that everybody like tries their way. And then when you hear my way, you can see how to tweak your way, but you have nothing to tweak if you don't, right? So that's why I'm really congratulating everybody who's put an answer in the private chat. They're starting to be different answers now. So it also shows me this is worth our time. I'm getting very different answers now. Some are like off by 1 decimal place. Some are off by actual numbers. So there's no shame if I can get a bunch of answers here, and I am now, so I'll shut up. So there's no shame in wrong. Okay, hold on. Okay, cool. I'm getting a ton of answers. 1, 2, 3, 4. Okay. Okay. Yeah, I'm going to intentionally, I'm not even lying. I mean, I don't want to lie. I've actually got 4 answers so far. Well, yeah, you can't even know. Well, I'll try to respond. Yeah, just take this as a personal acknowledgement. If you've sent me an answer, I see it and I congratulate you. And you should screenshot it or whatever and send it again. I want that, but I'm not saying if it's right or wrong, and I'm not going to personally start it because I want to. But some of them are, but they're not all the same. So some of them are right and some of them are wrong. But this is the question to all the rest of you on the board right here. And in fact, well, yeah, I'm going to pause for a second. And my highest recommendation, those of you who did do an answer, I'll say, if you did submit an answer, if you want to push this one step further, I would encourage you. So I can't tell you if your answer is right or wrong. Obviously, you can check, but then there's so much you can do. Convert your answer if you can. Those of you who have given me an answer, try to convert your answer into miles approximately. And I'll tell you right now, there's about, and I'll say this to the whole class, there's 1,600, approximately 1,600 meters per mile, like 1,600 meters per mile. That's just I mean, I just know that, and I'm telling you that. So whatever answer you got, and for every answer you got for the problem on my screen, you definitely got it in meters. Actually, I don't know, but I assume you got it in meters if you used like the 9.8 or the 10 meter per second squared number, which is a good thing if you use that. I'll say that again to everybody. I am assuming that the number 9.8 meters per second squared or 10 meters per second squared is fair game for you to use to solve this problem. Like, you should use that number to solve this problem. I think all the people that gave me answers did. That means your answer will be in meters, probably. So then I'm just throwing out there to keep everybody together that there's about 1,600 meters per mile. So if you've gotten an answer and you don't really know any further how to check if it's right, or you're very confident it's right or whatever, convert your answer, like in a sense, divide it by 1,600. See what you get in miles, and just back up and just ask yourself, does that seem realistic or surprising or not? It may be a check on your answer. It may just put perspective on your answer, but we're talking about dropping something for a minute, and for every, and now I'm starting to get more answers too. Cool. And I'm getting conversions. Thank you. Awesome. Again, those of you who are doing this, for some reason, I'm afraid to personally acknowledge because I don't want to say right or wrong, but I can definitely see. Yeah. Awesome. Okay. Right. Thank you for doing the nice. Okay. So all right, I'm probably going to do this for everybody, but I'd like, is there anybody, how about this? Could I just to make sure we're all together, could I just get a show of hands of people, if you understand that I'm asking us to try to solve this problem, if you understand that at all, whether you've answered it or not, but if you understand that I'm looking for us to try to solve this problem on the sheet, could you give me an electronic hand, please? That's fast. Oh, thank you. That's really fast. That's awesome. Oh, that's fast. Oh, wow. All right. Awesome. I believe you. Okay, great. That's a lot. Now, a lot of the people raising their hands are the people that did give me answers, but okay, but cool. But most of you, all right. So more, great. Okay. And now I'm looking in the chat again. Okay. Right. I'll start writing down some. Well, oh, two more people raising their hand. Sorry. And so, are you guys now raising your hand because I just asked you to, or do you have questions, David and Camille? If you have questions, please fire away. But if you're raising because I just asked you, you can put them down. Oh, okay. Okay. I'm going to. How do I want to do this? All right. I'm going to start by saying, I'm going to assume that if you didn't get an answer, like you're waiting for me to help. I mean, I'm assuming that. Yeah. No, I'm not assuming because you just told me. You all get that this is the question. I got a bunch of answers from some people. I'm very impressed. I guess I will shoot straight to I will cut to the chase and say, for one thing, yeah, I do think the answer, I guess I'll just say this. I do think the answer is like 18,000 meters. I do think that's the answer. I think that, and I'm going to show everybody how, obviously, and I think that means some people got it right. So some people may be doing it the exact same way I am, or maybe not. We'll see. I do think the answer is 18,000 meters. I do think a couple of things about that number. One, it's a nice even number. Like it's not a complicated number. So it sort of reveals that maybe my calculation wasn't too difficult or something. Like it's not like 18,427, like it's 18,000 meters, but it is 18,000. And that right away is a little bit interesting because none of the numbers that are given, like the numbers that are given are 60 seconds and V naught equals 0. And then if you read between the lines and you understand this is a free fall problem, you could say that the number 10 is given. But none of those numbers obviously lends itself to 18. So like the fact that I think the answer is 18,000 means basically what I'm saying is you could see that I did more than just go 60 times 10 or something. Like there's something going on. And that's why if I were in this class and I weren't the teacher, right? I mean, that's why I'm totally sympathetic that I easily, and many times I've been in physics classes where I'm sitting there. If I were sitting here right now and not totally getting this, I would be like 18,000. Like, where is that coming from? Like, what? Like, right. So there's something going on here that maybe is, but that some people have done. But I also, to show you where I got the 18,000, let me just check. Like, that's such a weird number. I got 18,000. Like, let me try to put it in perspective. So one thing is, like, I did happen to know there's like 1,600 meters in a mile. So I did ask you, or I thought, okay, let me divide this by 1,600 and just get perspective. And you do get, well, 18,000 divided by 1,600. I'm going to get a number a little bit greater than 10. Right? I don't know if you follow, like, and I'm intentionally trying to talk to you guys right now without equations. I'm trying to show you like how to be comfortable with numbers and think that, there's some estimation going on, but there's number sense here. And there's math and physics sense, right? Before we grind it, we're trying to have like a big picture feel. So I'm saying when I hear 18,000 meters, 18,000, maybe I think of that as 18 times 10 to the 3, like 18 with 3 zeros, I kind of think of it as. And then I say to myself, I want to scale that down to miles, just so I can picture it. If I say there's 1,600 meters in a mile, right? I'm in effect dividing 18 by 16. That's like 1. And I'm dividing 1,000 by 100, like 3 zeros by 2 zeros. That's 1. I don't know if I'm saying that weirdly, but this is why scientific notation, all those things actually help. They're not to make things more niggly and grindy. The point of scientific notation and things like times 10 to the 3rd is so that we can actually picture this stuff softly in our heads, that on Zoom, right? Like, so when I go, oh, 18,000, what's that? Then I go, oh, I got to divide that by 1,600. What I do in my head is I go, oh, that's going to be a little more than 10. That's going to be around 11. Like, it's not 1 because it's 8. Oh, sorry. I'm going to, oh, okay, cool. I'm seeing it. All right, cool. I'm totally seeing the, yes. Hold on, sorry. Hold on. But yes. I'm saying, oh, so I go, what's 18,000 divided by 1,600? And in my head, I go, oh, that's like, what's 18 divided by 16? That's about 1, a little bit more than 1, maybe like 1.1. And what's 1,000 divided by 100? That's 10. So it's like 1.1 times 10. It's like 1.1 with move the decimal point or with a 0. So it's around 11. Okay, so I'm saying before I even work this out, I partly to communicate with the people that have done some work here and thought through and want to know, and partly to communicate with all of you, any of you who are trying to get a hold on this physics stuff. Like I'm saying in my head, when I look at, I haven't shown you how to get to 18,000, but when I get 18,000, what that means to me is like 11 miles. And that means before I start calculating, if I think that the answer is like 11 miles, let me even ask myself as a physics, I mean, this is not a math class. This is supposed to be about the physical world. Does this actually add up to me? Like I'm saying, I drop a rock from a really high place and I let it go for a minute. In that minute, just naturally left to its own devices, just due to gravity, it would speed up and speed up and speed up and go so fast by the end that it would have covered 11 miles. That is what, if the answer is 18,000, as many of us got, then that's what that means about 11 miles. I'm not saying that's wrong. I'm saying, whoa, if that is, I mean, first of all, I'm saying I better think about whether it seems right or wrong. Otherwise, I'm not doing physics. I'm just doing math. Second of all, it does motivate me a little bit to want to actually solve the problem and prove whether it's right or wrong. Because if that is right, whoa, I need to see justification and I just learned something, I guess. But if it's wrong, I better see why. So I think it is right. But let's see. This is how I do it. Well, actually, well, yeah. Well, I'll write, I'm going to, oh, cool. No problem. So what I'm going to first do, I'm going to write down the equations that we have so far. Well, yeah. But yeah, I think the answer is 11 miles. So if nothing else, I'm now about to show you why I think the answer is 11 miles. But I can also point out, if those of you who are bored or do get all this or whatever, when I say 11 miles, which I do think is right, like I do think that's right, but I do think that's staggering. Like it's why I like physics. Like I would not think that that's right if I didn't know it's right. But I only know it's right because I believe the math that we can do right now. But 11 miles, I mean, 11 miles. But look back at like some of the values for G I gave you on Monday or Wednesday. At some point in there, I wrote like G equals approximately 22 miles per hour per second. 22, I wrote. But here I'm saying it would fall for 11 miles. That's something to think about. It all adds up in the end. But if you want something to keep yourself curious, you can think about that for a second. But anyway, I'm saying this. Sorry. Okay. What I've done here, and again, it's the same. We technically have 5 equations so far, I think, or we're actually 6. We just developed a new one too. But up until like a day ago or so, we technically had 5. In other words, we had 2 other equations that had limits written in them or derivatives. Very important, but I'm not even writing them down right now because those are the two equations that show how this physics is linked directly to the calculus, right? And that's super important. But even those two equations, we almost never like plug in or do anything with directly, because what they're really saying is, okay, take a derivative or do this mathy thing. So of the actual equations that we actually even work with directly, in a way, we just have the two definitions of average velocity and average acceleration, right? The two at the top. And then I make this super big point that seems very abstract at the time, probably like, or I try for 2 days to drag out this big point that's like always annoying while it's happening. This big point that says, if the acceleration is a constant, if our change is not changing, right, then we have this new equation, this new revelation, this idea that, and it's only true then. So it's our first, as I've said before, our first not triple equal sign, right? Our first equation that is not true all the time by definition, but in fact, this one is true some of the time under a certain condition. This equation says that the average velocity between 2 points in space and time, between two events, will be the average of the lowest and highest velocity, or in other words, the first and last velocity, or really any two velocities you want. If you average them together, if you add them together and divide by 2, you'll get the average velocity for that interval, if and only if velocities are changing in a constant way, right? Like that's what this last equation says, okay? But the reason I make a big point of it is because, first of all, it's true a lot of the time. It's true whenever acceleration is a constant, which means whenever there's free fall involved, for starters. So it's always applicable during free fall, and we're in free fall right here. But also then when you put that equation together with the other two, you get a very powerful, complete, like package of prediction for any accelerating object. What I'm saying here, so now I'm trying to say it in a slightly different way that I haven't said it before. I'm saying we really only have these three equations to play with. I mean, in terms of doing stuff, we have these three to play with. But there's a lot of play there. If you look at the first equation, average velocity equals displacement over time, right? That's true always because it's a definition, but just rearrange it and it says displacement equals average velocity times time. In other words, what some people interpret as distance equals rate times time, right? Hold on, I'm just changing something. Sorry. Okay. But then the second equation now. Okay, here's where I am right now. Right here. And all of what I'm saying right now is try to justify and ultimately show that the answer is 18,000 meters. Okay. And there's a million different ways to see that. But it is worth spending, like, there's nothing special about 18,000, but there's something very special about this problem. Because once you can do this kind of problem, whether I say 60 seconds or 10 seconds or 1 second, like once you get how to do this basic kind of problem, it opens up a lot of physics in various directions. Trust me, please. So I'm dwelling on it a lot. And again, I'm recognizing that a lot of you already understand the answer to this problem, but I'm trying to show you many different ways to see that answer. So the more you're less confident, of course, please listen and please understand that I know this still needs talking about. If you're confident, what you should be trying to do is hearing as many other new ways of seeing it from me as possible. Like the more confident you are of your correct answer, the more flexible you want to try to be, honestly. And those of you who are not there yet, like we're going to get there. So I'm now about to say something I don't think I've said at all for 3 days to any of you. Okay. I want to look at this second equation, the average this second equation that I just bubbled in red. Like, so this is like a please tune in moment, even if you've been tuning in. Like this second equation, average acceleration by definition. Whoa, sorry, my whole computer is about to, I did not realize it was not plugged in. Hold on, I'm sorry. I knew something was funny. Okay, sorry, it's nice that they warned. Okay. This second equation, average acceleration, is defined as change in velocity per time. Like that's what it means in English. And I think that is an English concept, right? It's a definition, it's a triple equal sign. It's always true. It's just what we mean by acceleration is change in velocity per time, right? Okay, but notice you can rearrange that equation. Mathematically, I think you'll all agree with me. You can multiply both sides by t, of course, and you can add v naught to both sides. Like I think you are all comfortable from chemistry and stuff that, like, whenever you get an equation in a science class, if that equation is truly true, then it's true, and you can like rearrange it to solve for whatever you want to solve for at any time. So all equations are truly like many equations packed in one. And I don't think that's new or surprising to any of you, but let's actually analyze this step. If you rearrange this average acceleration equation, you do get a piece of like handy knowledge here. I mean, what this is saying in English right here. Okay, you can barely read my handwriting, but what I'm saying on the right side, what I'm trying to write out here on the right side, where I just took the average acceleration equation and I just rearranged it, and I wrote v equals at plus b naught. What that is, okay, it's not new knowledge, right? But it is a new perspective and a new handy way. It's saying if you ever want to know the final velocity of something, like if something's speeding up and up or slowing down and slowing down, and you know how fast it's going like right now, and you want to know how fast it's going a little bit later, how fast it will be going a little bit later, well, just ask yourself how much later and multiply by the acceleration rate. Oh, and then add any head start that the thing might have had velocity wise. In other words, what this thing is saying, like, it's almost more logical. Some of you may understand this equation off the bat, like better, like it might actually ring more true to some of you than its original form. And that's fine. And that's why I'm saying it, if that's the case. What it's saying here, in other words, it's saying, look, if something gains 5 miles per hour every hour, if it gains 5 miles per hour every hour, and it starts with nothing, how fast will it be going? In 3 hours, we'd say 15 miles per hour. If it's gaining 5 every hour and it starts with nothing, then 3 hours later, it'll end up with 15. If it starts with 2, then 3 hours later, it'll have 17, right? If it's gaining 5 every, I don't even remember what I said now. If it's gaining 5 every hour and it does so for 3 hours, it gains 15. So then just add on whatever it started with, say 2, and that's how much it has now, right? If I have 3 eggs in my pocket, what? If you, I don't know what, if, why do I have eggs in my pocket? If I make $2 a week in my salary, right? So every week you give me $2, then in 3 weeks you gave me a total of $6. Is that how much I have in my pocket? Well, yeah, if I started with nothing in my pocket. If I started with $1 in my pocket and I gained 6 from my salary, then I now have 7. That's literally what the right side is saying, right? Okay. And I'm trying to make it, that's what the right side, that's what this is saying. So now why do I care about all that? Because that's really how I do a problem like this. What we really end up doing in the end is saying, going back to this question, if I say, sorry. So going back to this question, what's known in this question okay, just to be as clear as I can, on purpose, the question on the first page is posed basically in English. If I really want to be cool, what I really should have said is, I drop a rock from rest, let it fall for a minute, right? Like, that's pure English. There's like not really a number to be seen there. If I just say that, let it fall for a minute. But even that English sentence, actually, if you know enough little physics, there's like 3 values that are being stated right away by that. Like, if the rock dropped from rest, then it's starting with an initial velocity of 0. If it fell for a minute, then its time that it fell was 60 seconds. And the key knowledge, the only piece of actual empirical knowledge that we're holding ourselves responsible so far as physicists, is we know if someone says free fall, that means constant rate of acceleration of 10 meters per second squared. Like, and I'm not talking about positive, I'm just saying that number 10, like free fall, it doesn't mean some certain rate of velocity. If something's free falling, its velocity will always be changing, but it'll always be gaining or losing velocity at a rate of 10. So the problem that we're solving right here is we know these three numbers. And what are we looking for? We're looking for X. We're looking for living all the wrong places. We're looking for X. We have the equations to do it if you want to think in terms of equations. But I'm really trying to stress, like, the equations shouldn't do the thinking for you. The equations are just shorthand for thinking that should make sense, i.e. we're looking for X. So what I can say is, okay, so I'm up here now. Displacement equals average velocity times time. Displacement equals average velocity times time. No one told me the average velocity of this falling object. I don't just automatically know that just because it's falling. I know it's acceleration, but average velocity. If this thing is gaining velocity at a constant rate, it's like those numbers that are getting higher and higher always by the same amount. If this thing, this falling rock, is truly gaining velocity by the same amount every second, then I can believe this equation. I can believe that average velocity will be the average of the velocities. Like the average velocity for the whole 10 seconds will be the average of the very first velocity at 0 seconds plus the very last velocity at 10 seconds divided by 2. Like I believe that because I believe the numbers are increasing in a pattern like that because it's gravity, free fall. So if I know the very first velocity, it's 0. All I need to know is if I just knew the very last velocity, I could average that with 0, then I'd have the average velocity, and then I can multiply by time and I could get this answer. And that is really what I'm doing, because I say to myself, self, you need the final velocity. If you want to get this average velocity, you need a first and a last average. Now, again, sometimes you can't even get away with that, but you can with free fall. So yay. I just need the first and the last to average together. So I just need the last. I just need that final maximum velocity. Why does it have, like, how can I get it? I don't know it. Nobody told it to me, but it's gaining velocity. We call that acceleration. The very last velocity it has, this is why I'm making a big deal of this, the very last velocity it has is just whatever amount of time it's been falling times that rate. In other words, plus whatever it started with. So what I'm saying is, in my head, right? I mean, what I'm saying is, we'll go back to that. Here's it. Like the initial velocity, we were told was 0. It's not always 0, but we were told it's 0 here. So the final velocity will be so the 600 number, right? Now, I know I've said this before, but like, so this 600 number, which is like the first number that pops into most of our heads when if we see a problem saying it's falling at a rate of 10 meters per second squared and it's falling for 60 seconds. Of course, we all want to multiply 60 by 10. And it's the right thing to do. We just want to know what we got. When we do that, we didn't get the final answer. We got a step toward the answer. When we multiply 60 by 10, what we're saying is, oh, for 10 seconds, sorry, for 60, every second, this thing is gaining 10 units of velocity. So after 60 of those seconds, it gains 600 units of velocity. It started with 0. It gained 600 units of velocity, 600 meters per second. So that's how fast it's going at the final moment. Like, this is where a lot of people will accidentally or under stress or whatever stop and think, oh, that's how far it got, 600 meters. Like, no, we're not there yet. This is how fast it's going by the bottom, by the end, by the 60th second, right? So this is that V. So then we can say, oh, we can go, oh, so the average velocity is the average of two velocities. It's the average, and notice divided by 2, like not divided by t, divided by 2, because I'm just literally averaging velocities, adding them together and dividing by the number of things. And the number is 2. 0 plus, so we get this. So it's 0 meters per second plus 600 meters per second divided by 2, right? And we get 300 meters. So this is the key now, right? Really, if you get this, then you're getting some physics now. Like, if I drop something for 60 seconds, I'm not still done with the question, But what I've just now figured out or inferred is, oh, something that's falling, free falling for 60 seconds. It's never falling at the same rate for any two, like at the beginning, it's falling not at all. Then it's falling like 1 meter per second, then 2 meters per second. Like it's faster and faster and faster. But the middle velocity, the mid velocity that it'll attain for those 60 seconds is 300 meters per second. And that's its average velocity. Like it will spend an equal amount of time going slower than that as it will going faster than that. So a free falling object that's going through all of these velocities on average is going 300. So it's equivalent then if we want to know how far it goes, we do displacement equals average velocity times time, distance equals rate times time, right? And we go, okay, we go back to this, we say this thing. Like I'm just redoing that again, just so you can see it, but, and the time, sorry. Right. Like, so where the 18, so this is the answer, first of all, this is in meters. It will fall 18,000 meters. That's a lot. And it does turn out that that's like 11 miles. But 18,000, where that really came from, what's 18,000 really mean? It's really 300 times 60. And 60 as in the 60 seconds. And what's the 300? The 300 is the average velocity, the average. Where'd I get that? What I really did was I took 0 and 600 and added them together and divided by 2. If you tell me that something's free falling for 60 seconds, in my mind, I right away go, oh, so its final velocity is 600 meters per second. So its average must be 300. Oh, so it would fall 300 times 60. Like, or if you say to me something's free falling for 7 seconds, I right away say in my mind, I'm like, oh, so its final velocity is 70. So its average velocity is 35. So it would fall at an average rate of 35 for 7 seconds. So it would go 245. Like that's what that is. Seven times 35 is 245. So it would fall 245 meters. Like I do that in my head. And I'm not trying to like boast. Well, I'm kind of am. It took me 50 years. Like I'm glad I can do something with my life. So I can do that in my head. But you can do that in your head. And I think some of you already have. But notice when you do it in your head, if you do it that way, what I'm not, well, I'll go on a second. I'm not plugging into equations and squaring things in my head. Like that's just as hard for me as it is for, like I can do that actually, but I don't want to do that. When I say I'm doing these things in my head, I'm not actually taking out formulas and plugging to, I'm doing the formulas in my head because I get right. And that's what we want to do. Like there's a famous Italian-American Nobel Prize winning physicist named Enrico Fermi. I mean, he's dead now. But I mean, he worked on the atom bomb and stuff like that, but very brilliant physicist. And one of his big things that he taught generations and generations of physicists was he literally, this is how he felt about math. His point was never ever do, and he was great at math, of course, but his point was never do a calculation, never sit down to perform a calculation until you're already pretty confident you know what the answer should be. Like now that's bold. I mean, that's kind of extreme, but that's the idea though. So wait. All right, so going back to this is what I think the answer is. I do think if you divide that by 1600, you'll get like 11. I do think that's correct. Something, and I'm going to show you this yet a different way another day. But it is true that the constant acceleration due to gravity can also be written as 22 miles per hour per second. And if you really think it through, you'll see how that actually does mean that in 1 minute, something should fall not 22 miles, but 11 miles. Put one other way. Oh, actually, let me ask everybody. I'm going to pause for right now. I'm going to pause for a second. Based on this, I still want to do more, good or bad. I want to put these into another equation and another equation in a second. But just based on all this, if you're following this, let me pause and ask, how far would something, and just put answers in the chat. You can put public, private, whatever. But I want to know, based on this, I'm going to ask the exact same question again now. But how far would something fall free fall from rest in 1 second. In 1 second, how far does something fall in 1 second of free fall from rest? This is not a race, but this is a, like, I want to see it. And I'm seeing something in the, I just see something in the private chat, which was right and correct. Awesome. So anything I say in the private chat, I'm not going to say if it's right. I mean, you can put it in the private or the public. This is awesome. So that's awesome. That one person, thank you. And it's right. So he can go get a beer or whatever, or she can go get a beer. But I would like to see from everybody. I'm going to repeat the question. And again, you could put it in public or private or whatever, and you shouldn't be ashamed if you're wrong, but you should try to get this. It's the same question, but I'm pairing, but frankly, it's less computation. I'm saying, here's the question. So this is the question to everybody right now. I think. Okay. Now I almost feel like a teacher. I almost want to say that teacher thing of like, oh, it's the same 5 people again. It's not exactly, but it kind of is. I'm psyched. Like like I will say, I mean, 5 people is 5 people. I'm going to assume that I'm going to assume that this is worth it. I mean, in other words, I'm going to assume that anybody else who hasn't given me an answer to this question yet is hopefully still thinking or struggling or something. Like don't just totally walk out of the room, just don't go radio silent for 7 of these examples, because then it really will get redundant for everybody. But this is, all right, you know what? I'm going to shift. I always feel so defensive doing this because I think it is really important, but I think it is intimidating at first. But like it's a stand. I'm stalling slightly to see if anybody else wants to, but I think the answer to this, I don't know if I'm scaring people away, But I'm trying to say over and over, free fall means and especially free fall from rest. That English expression, like put it this way, if you ever saw that on an exam, God, if you ever see on a physics exam, free fall from rest, what it automatically does mean is constant acceleration of approximately 10 meters per second squared and initial velocity of 0. Like that's a lot of numerical information that just automatically like understood from those few English words. So if nothing else, I'm just trying to highlight to everybody from here on in physics, if someone says like dropped or free fall or anything, you can just go, oh, constant acceleration, oh, 9.8 or 10, and you can round to 10. Like, but it's also, it goes both ways. We're going to assume you know that if we use those phrases. So I definitely think at least 5 people in the room do get that. Further, but again, if we say rest from rest, that means V naught equals 0. Like you can write that down. Now past that, the only way I can really vary a free fall problem, well, right now I'm just varying the free fall problem by saying how much time the thing is falling. But I am trying to get you all used to the idea that this is a problem you should be able to solve, like no matter what number of seconds I plug in. Like it's kind of a drill and chill kind of, a drill and kill kind of exercise at a point, after a point, like we want to get past the sum. So I'll say again, for example, so 10 is always the number that you know. That's the habit I'm trying to build. But the habit I want to break at the same time is whenever you multiply things by 10, don't think that's the final answer. Like for example, right here, when I say how far does a rock free fall from rest in 1 second, I agree with all the people in the private chat that told me it falls 5 meters, not 10, 5 is what they all ultimately told me in the private chat. Like, even though I'm totally using nothing but these numbers down here in the right corner, I'm getting 5 out of that. They're getting 5 out of that. Because we're all understanding that constant acceleration means velocities are changing. And the way to get displacement is to go through, at least if you're going to understand it, through average velocity. So if something falls for, so if something falls for 1 second, if it falls for 1 second, that means it builds up speed for 1 second. It builds up from 0 to 10. So 10 means it's the final velocity that this thing is going at the end of 1 second. At the end of 1 second, it has just achieved an instantaneous velocity of 10 meters per second. That's very fast, but it's only been going that fast for this moment. It's never gone that fast before. It's always been going slower, slower and slower. In fact, at the very beginning, it was going 0. Now, it would be false to represent this entire journey as a 0 velocity object because mostly it was going faster than that. It would be equally false to represent this object as a 10 meter per second falling object because it was almost always going slower than that. It's fair only if you're going to pick one number, if you're going to pick, and this is like averaging, like giving you an average grade, like if we're going to pick one number to represent all the variation, the one number that we think, like what is an average? An average is a lie. An average is a falsehood. It's the one falsehood that we think is the least false out of all possible falsehoods, right? When we say that you got a 93 average in this class, we're saying, yeah, every day it says, oh, she got a 93. Now that's a lie. You didn't get a 93 every day. But what actually happened was you got an 87 on one day and you got a 99 on another day. So we say it's as if you got a 93 every day. Like we ripped you off. You had a 99 one day, but we're like, you're like a 93 person. You're like, what? You just janked me out of 6 points. I got a 99 one day. We're like, yeah, it's true. But the other day you got an 87. So we just kind of gave you 6 points. So we gave you as much as we janked you out of. So we're calling you a 93 person. Like that's what an average is. It's a lie that is equidistant from all truths. That's actually what I meant to say before, right? An average is a lie that is equidistant from all truths. So it's the one lie that we get. And what's the lie? We're pretending that something was constant when it wasn't. But we're picking the one number that we can get away with that. We're saying this object that was speeding up from 0 to 10 was equivalent to an object that was always going 5. That's what we're saying, right? And this object did that 5 for 1 second. It went on average 5 meters per second for 1 second. So it traveled 5 meters. I mean, that's the answer to this one on the board here. And the other one, like it was speeding up from 0 all the way to 600 meters per second. So on average, it went 300 meters per second, but it did that for 60 seconds. So we multiply those, right? So we got to understand the difference between average velocity and instantaneous velocity. Like that's kind of what's going on here. But I'm psyched again. And I know a lot of you are totally following this and just like not putting things in the chat. That's totally cool too. I do understand that. I'm not, but again, I think this is all me just being desperate that we're on Zoom, because it's easier to do this stuff if we're all just like sitting, in a circle grinding, and I don't know. But so I'm going to go a step further now. I'm going to show you now, like, I think these are the answers. I think in principle, and sometimes this happens some semesters, like I might every day start class for a little while with a drill exercise like this, like for a while till, like I could just walk in and say, how far does an object fall in the first 5 seconds of free fall? Okay. And the answer would be 125. Yes, that's right. Okay. And you'll be able to do that. Like, you can check me, but we want to be able to do that by the end. Or if I say 8 seconds, I think the answer is 320. Is that right? Yes, it is right. Okay. And I didn't square anything to do that. But now, speaking of squares, there's another way to think about these things. And some of you are more comfortable with this, and that's these other crazy equations. Okay. What I'm talking about is this. What I'm talking about is, if you look back, like, to essential, I'll talk about that. Right. If you look at this mess of a page, I was trying to say, okay, we've got these 3 equations. We can use the 3 equations what I was really trying to say on this page is, if you want to get an answer to a free fall problem, you can, based on the 3 equations that we have. And not only that, you have to use all the 3 equations that we have. This is sort of also an illustration of why we've had to build up this knowledge. Like, at this point, I think it's a nice, cool, simple, straightforward problem. Like, how far does something free fall in 7 seconds? Like, at this point, I'm saying that's something we can do in physics. But no, we could not at all do that unless we had all 3 of these concepts. Like, we are putting all 3 of these equations together to get the final velocity of the thing, and then average that with the beginning velocity to get the average velocity, and then multiply that by the time to get the total. We are using all 3 of these pieces of knowledge: the definition of acceleration, the definition of velocity, and this property about average velocities working out nicely the way they do when they do. So we used all 3 of those pieces of knowledge. It may be why this is a long process and intimidating and boring to some of us. So is there a shorter, cleaner, faster way? Sure. As long as we don't like cheat ourselves. The faster way is to smash these 3 equations together once in one time without any numbers, and get one equation out of it, and then never have to go through all this again. And for sure, I think some of you have seen this or are doing something like this. What I'm getting at is this. And even though I have done this once for you guys, but I did it in kind of a rushed way, so it's totally, presumably no one knew what was going on. So I'm saying, okay, what everything we've been talking about for 3 days boils down to, I mean, in strict mathematical or general terms, what everything we're saying for 3 days boils down to, if you know something's acceleration, like, oh, sorry. Sorry. All this boils down to, if you have some object and you know its acceleration, and like, you know it, meaning it's not going to change, it's a constant value. Like, if you know that whatever the acceleration is at any given moment is the same as what it was at the beginning, if you know that, and again, free fall is the classic example of this, but if you know something's acceleration and you know for how much time it's been traveling, and you know at what rate it started off traveling, can you figure out like how far it went? The answer is yes. Like, that's what we've been doing for 3 days. We're now, what we're basically doing is saying we can apply distance equals rate times time, even when the rate that we know is an acceleration rate. We can do something like that. but what we're doing involves many more steps, and it's not just one equation, distance equals rate times time. Can it all be captured in one big equation? The answer is yes. Like if we put together what we've been doing, what we've been saying, so can we get x as a function of a, t, and v naught? Like lowercase f means as a, sorry. Right, so can we get x if what's given is a, t, and v naught? And then can we get it for all time? And what we're showing ourselves is yes, we can. The steps that we've been going through is what we've been saying is, well, we're saying, well, x displacement like total displacement equals average velocity times time. That's what we said. And average velocity, we're substituting in and saying it's the average of velocities, right? This is what we're doing. I'm go on the next page. I can go back if anybody asks me. I'm just recording. What we're saying so far is this, right? And then what we're saying is, and so now I'm doing this abstractly without numbers. I'm following the same process that we just followed. I'm saying, oh, our final velocity we tend to get by saying that it's the acceleration times the time plus the initial velocity. That was the thing I was saying about the eggs in the pocket or the stuff like that. So we're saying right? I'm just doing the algebra. I'm just expressing in algebraic terms what we've been saying. If we substitute that final velocity in, if that's how we get the final velocity by doing acceleration times time, then we can substitute that in. We can collect like terms and say, so just to be as clear as possible and as I can, and I know we have 5 minutes, I think, I'm saying that, so this definitely is now, and I, again, granted, I think I've done this maybe once before, and so we have technically added, but this equation counts as part of our equation list. In my mind, technically now this is, this is equation number 6 of our cumulative list. And this is a double equal sign. This is a double equal sign because it's not always true. It's not the definition of anything. It just turns out to be true. It is true if and only if acceleration is a constant. Partly you can see that right away because there's an A in the expression. Like if A were changing all over the place, what A would you put in? You wouldn't even know what A to put in. So there has to be a constant A even to put in. But also we only derive this equation from the other three, from assuming, like we put together three equations, one of which was only true if A is constant. So this equation is also goes under the heading like if and only if A equals A naught. But this equation now and I want to make it clear again, like some of you, some of you have seen it before and some of you haven't. Some of you used it to do homework questions. It's all fine. Like I'm not saying it's illegal, but now I'm saying it's totally legal and fair game for everybody. But now I'm also saying if you're ever going to use this equation, like, and when do you use it? You use it when you know the time, you know the acceleration, you know the initial velocity, and you're looking for displacement. That sounds like very obscure set of conditions, but really that's basic physics. Like someone names the time, you're looking for the space. The one catch here is we're saying if what you know is constant acceleration. In fact, let me even say that. This is often known as the constant acceleration position function. This is how you predict where stuff is going to be if you know that it has a constant acceleration. And you're welcome to plug and chug into this like with reckless abandon from here on in. But at all times, you should understand what you're doing. Like you keep the perspective on what you're doing and don't just blindly follow it. But here, what this is often known as. In other words, this equation does apply whenever there's any kind of constant acceleration. If it's gravity, then the constant acceleration value will happen to be 10. But there could be tons of other reasons that there's constant acceleration that don't have to be gravity. They don't have to be 10. So this equation is just true either way. Wait, it's 3 minutes. I know there's 3 minutes. Oh yeah, actually, because let's leave it at that. There's 3 minutes. I'm happy to take any and I kept saying that there would be, sorry, can I just say this Monday's spring break, correct? I mean, like we don't have class this Monday because of spring break. Is that correct? Okay, cool. That was fast. I knew you knew that one. Okay, so I kept warning or cautioning you or that there might be one more homework before the exam. Forget it. There won't be. I mean, I will start tying loose ends together and trying to post solutions. Like there's still some problems probably that we didn't talk through. So I'll see which ones they are and post solutions, stuff like that. And I'll start getting together the practice midterm that I will post for you at the end of spring break, right? But no, I can't believe I just said that. Yeah, I just said there'd be no new homework. Oh no, it is definitely not. Oh no. Wait. So for everybody, it is definitely not too late to hand in any homework, especially not 4 and 5. It is definitely not too late. And I want to say to all of you, like, right, if you're going to do anything I don't want to invade on your spring break, but if you're getting yourself together or knowing that there's an exam afterwards, definitely handing in 4 and 5 now would be a very good thing. I will give you credit. Number one, they're not late. Number two, those would be probably the best things to be sort of studying and refreshing and trying to work through now that we have all this. Like, so all of you, yes, that just, the question I just got in the private chat was a perfect question because I was just regretting my decision to not give you any new homework, but now I don't regret it. I will not give you any new homework. Please do catch up on anything in it. Like, take this opportunity to catch up and then I will post a practice exam that will take you through this material and wherever it takes you, that's what the actual exam will look like, blah, blah, blah. Yeah, no, good. So with that said, since I've rushed a couple other endings before, I'm good. If you guys are good, if you say goodbye, we're good. We'll take the next class and have a great break. So bye. Oh, yes, thank you. Enjoy your break. Thank you. Goodbye. Enjoy your break. Bye. Bye. Good to see you. Bye. Thank you very much. Yes, enjoy your break. Excellent. Bye. Awesome. Bye. Great. Yes, see you after break. Right. Yes. Awesome. Bye. Thank you. Bye. Awesome. Bye, Jennifer. Thank you. And Michelle and Aja, you guys are okay? And Luna, you guys are okay? We're still there? Or cool, cool. I'm gonna go. That's all right. I'm going. You guys are good. Michelle, Luna, and Aja, you're going once. Or do you want to copy the notes? Can I go? Should I go? I'm going, going, going.